Hello, I'm David Doughty, and I'm chairman of the History of Hydrology Committee of the American Geophysical Union. We're here in Boulder at the quadrennial assembly of the IUGG and of the IAHS, the International Association of Hydrological Sciences. We are lucky enough to have here with us Professor Jim Dooge from Ireland to participate in our oral history project of the American Geophysical Union. And I'm going to interview him on his influences over the past 40-some years in the history of hydrology. So Jim, to start off, why don't you tell us about your school, your degree, how you got started?
I graduated from University College Dublin in 1942. I took two bachelor degrees in that year, one in civil engineering, which of course was largely structural engineering, the other one in mathematics, mathematical physics, and geology. This was a BSc degree.
Mm-hmm. Somehow you got involved in hydrology from all that. How did that happen?
Well, of course I had to get a job, and the first job that I got was working with our Office of Public Works. They were responsible for main river improvement works, both for flood prevention and for improved agricultural drainage. And apart from surveys during the summer, I was assigned during two successive winters to do hydrometric survey work. I think that was excellent training. I had to try and feel the pulse of these rivers in order to get a full stage discharge curve of them. And of course I became curious about hydraulics and hydrology as it affected river flow.
Yes, I think that speaking as an old stream gauger myself, I think that that's the best training you can have for getting interested in hydrology. And I believe that every PhD, as soon as it finishes its degree, should be sent to a river and for a year watch the river flow. So where did you go on from there,
Well,
Jim?
maybe I should say, you say he should be after his degree. I'm not so sure he shouldn't be made do it before his degree, that it shouldn't be like a language requirement. Many universities have a language requirement for their PhD. Maybe we should have a flow measurement requirement to get people close to the rivers themselves.
Very good idea. And what did you start doing, your first jobs in hydrology?
I worked for 3 years of that work, and then I went to our Electricity Supply Board, which is a national authority, and I worked in there in what they call their hydrometric section, but it was concerned with all the hydraulic and hydrologic work in the design and operation. And there I dealt with problems like designing the diversion works during the construction of hydro plants, estimation of spillway design floods, also question of cooling water intakes and outlets for steam power stations, so that in general I had to know more about hydraulics and hydrology.
But you started out actually then in hydraulics and went into hydrology from there. Your first interest is in hydraulics.
Essentially, and for a long time. Indeed, throughout the 1940s, throughout the first 10 years of my career, I was interested in both hydraulics and hydrology. I became quite curious about hydrology. And at that time, there were no textbooks. You couldn't go to a library and look at a row of 5, 6, 10 general textbooks on hydrology. Mead had written a book in 1919, but in the mid-1940s, there was a rush of textbooks at that time. I learned my hydrology, educated myself as a hydrologist at that time, from a number of sources, and there were two main ones. One were the water supply papers of the USGS, and from this I learned about unit hydrograph methods. There was a textbook by Hoyt and Grover on river discharge, which of course I read at an early stage. But then On the question of hydrologic processes, I quickly found out from the university library and through our meteorological service library that the place where hydrology was being developed was inside the AGU. So, in fact, at quite an early age, I became a member of the AGU so that I got the proceedings rather than go look at them in someone else's library.
And you received several honors and awards from the AGU through the years, including fellow and what other awards?
Well, I got the Horton medal for a paper which I presented on the general theory of the unit hydrograph, which appeared in JGR in 1959, and then I afterwards was made a fellow and indeed received the Bowie medal from the AGU, and I was proud of that in a double sense. Firstly, it came to hydrology, and secondly, it came to me.
Yes, both quite fitting. Well, as I remember, we first met in the 60s, and it resulted mainly from your interest in linear systems analysis. You essentially introduced linear systems analysis as a tool into hydrology. And how did that come about?
That came about, I wrote a thesis. I went to the University of Iowa for 2 years as a research associate. For tax reasons, I wasn't able to register as a PhD student. And I took another master's degree, attending PhD courses as well as doing my research work. And in my thesis, I dealt with the hydrological problem. The topic was unit hydrographs based on triangular inputs, or triangular time area curve, if you like. I used the hydrologic thinking of the day in regard to that. And when I had finished and got my degree, a casual remark by a mathematician friend made me realize that the whole of the unit hydrograph approach was essentially an assumption that in acting on rainfall, the catchment was acting in a linear time invariant system. And that's what I put down on paper for my 1959 paper. There was a second element that came into this. That was the first part, the first ingredient. Second ingredient was that I worried about the question of flow routing. And of course, the popular method then, and it still survives, was the Muskingum method. And if we take x equal to naught in the Muskingum method, then we have a pure reservoir action. If we take x equal 0.5, we get, not exactly, but we get to a second moment approximation, we got pure translation. And here we find hydrology was working on something that was a transition between a pure linear storage element and a pure linear translation. Now, the second ingredient into my 59 paper was something that struck me just as I was about to go to sleep one night, that why do we have to have a transition? Why can't we copy what the electrical engineers do with a length of wire which has a certain resistance all along its length, has a certain capacitance all along its length, but they, in their analysis, lump both of those. They have a lumped resistance and a lumped capacitance. So I said, well, why can't we have, as it were, a lumped translation, pure translation, and pure reservoir action? So the 59 paper was a combination of those two, and that opened up the idea, okay, we're dealing with linear systems. There's some analogy to the electrical system. So I went off to the library and read a whole lot of books on the theory of electrical circuits, and came back and applied that to hydrology.
Yes, I remember reading your paper and having, soon after that, or perhaps just before I read your paper, I had gone to Stanford and taken a course in linear circuit analysis. And it seemed to fit in so well that it was, you know, everything from electricity and electronics turns directly into your framework, and therefore there was a lot of information that could be transferred directly, much as Tice did in groundwater on the heat flow to groundwater flow. Well, that paper had a tremendous impact on hydrology. The hydrology of that day was sort of turned on its head, and everyone became interested in linear systems analysis, whether they understood it or not, of course. And it led to some other things. I remember there were short courses, there were papers galore. There was an excellent series on linear systems analysis that was published from Wageningen, and then the Committee on Mathematical Models in Hydrology grew out of, to an extent, the burgeoning of interest in scientific hydrology that grew out of that paper. So how did this committee occur first, and what was its purpose? What were you up to when you started? Give us a little history on the...
Looking back on that, it probably, looking back on the pure record of it, it seems to be a series of accidents, but it probably was something waiting to happen. But how it actually did happen, I got a call from Peter Wolf, Imperial College in London, saying that he had an American visitor coming in, one Jim Amorocho. The name, of course, was familiar to me because he had presented a year or two before his classical attempt at the nonlinear analysis through the Volterra series approach. And the inquiry was that he wanted to come to Ireland to see both myself and Professor Eamon Nash, who is also active in this field, and could we both meet him together, either in Dublin or in Galway. I made the counter-suggestion that if he was coming to Imperial College, why not set aside 3 days that Professor Nash and I would travel to Imperial College, and that we would have a 3-day session. Interestingly enough, that was a session in which we got together the first day. We brought the students in on the second day, and then on the third day we sort of got talking again. Now, there was Professor Peter Wolf and Professor Terence O'Donnell, who has since made many contributions in this field, were there. And Jim Amorocho had, on his way to London, visited Wageningen and met Professor Dirk Kruijnhof van der Leur, who had also done some interesting things in regard to the response of groundwater, viewed as a linear system, and introduced the concept of a reservoir coefficient, which was a significant amalgam of all the parameters, 3 or so parameters which were involved. So we had this meeting, and we became a sort of informal college, corresponding with one another. And this, of course, is very typical in scientific work. But also, inklings were coming through that some interesting work was being done also at the University of Moscow by Gennady Kalinin, and there was the classic paper on flood routing by Kalinin and Milyukov. Now, I visited Leningrad in about 1965, and again, it's interesting that the meeting was not a hydrology meeting. It was a meeting of the International Association for Hydraulic Research. And at that meeting, again through an accident, I managed to contact at an early stage Gennady Kalinin. And there was a meeting then over drinks and snacks, which lasted the whole morning, between Gennady Kalinin, his collaborator Milyukov, and Lev Kuchman, who at that time was probably only a postgraduate student of Kalinin's, and also Dirk Kruijnhof and myself. And we discussed then how we could exchange information about the work going on in the Western world and the work going on in Eastern Europe. Professor Kalinin made it clear that the operation of their system meant that they could not operate in the informal way in which we'd been operating, and therefore it was necessary to have an umbrella organization. I returned. I discussed the question with Jose da Costa, who at that time was running the International Hydrological Decade. It hadn't become a long-running program at that time. And he was very sympathetic, but unable to fund us directly, but was prepared to fund us indirectly through the International Association of Hydrological Sciences. A good deal of lobbying, organization, resulted in us getting the matter onto the agenda for the General Assembly of IAHS, a General Assembly like the one we're having here in Boulder, in 1967. And
That was at Bern?
That was at Bern. And the committee was chaired by Walter Langbein, and that committee made a recommendation that there be established inside IAHS a committee on mathematical models. And indeed, that committee, as you well know, consisted of a remarkable trinity, with myself as chairman, Kalinin as vice chairman, and yourself as secretary.
Yes, a happy trio.
A happy trinity, yes, no division.
A trio now.
Trio.
Now let's keep religion out of this. But yes, it was a good group, and I sort of was dragged in, luckily, by Walter Langbein and by you. However, I also had worked with Terence O'Donnell. He had come over to the States and worked with me in the USGS for a year just before that. And he was an integral part of this group also, was he not?
Terence was very much an integral part of this group. At the time when we had this informal group, Terence was the center, the node, a sort of informal secretary to the group. And indeed, his contribution during that period was absolutely crucial and shouldn't be forgotten. Of course, Terence and I, we had met sometime casually and briefly in the early 50s, but in the early 60s, by this time I was a professor at University College Cork. Terence was at Imperial College London, and we were in quite close touch. Indeed, Terence's ideas had influence on a number of my own ideas, but also he had at that time, and subsequently, was always a marvelous person for reviewing anything you had in mind. If you had an idea or a draft paper, there was no better person to get his opinion.
And this group led to a series of meetings for the interchange of ideas, and at each of those meetings you presented papers, ideas, stimulation. What other contributions do you feel you were making other than these political sort of ones, which we'll also discuss? Scientifically, what do you think were your major contributions during that period?
Part of it was a philosophy. You've already mentioned the fact that my 59 paper had an influence in changing thinking in hydrology, and I'm proud enough to agree with you on that point. And one of the things it did was change the language in which these things were discussed. I think this was terribly important. But the philosophy was which was sometimes misunderstood by some research workers in hydrology. The philosophy was a search for a simplicity that was a rational simplicity. Not as the simplicity of crude assumptions or assuming the difficulties out of the way, but more a question of, can we break down the problem and make an attack on it? There's a famous algebraist called Polya, and he's done excellent work in algebra, but he also wrote a little book about how to solve it. And that's something else that every hydrologist should read. Because Polya has a number of maxims here, and this thing can be read by high school students as well as by professional scientists with profit. He says here, if you are in a real difficulty in regard to a problem, don't bother to solve it. Go away and solve a simpler one instead. Of course, the problem is, how do you choose that simpler one? But he says, if you choose that simpler problem right, and you manage the solution to this, then you are better armed to come back and attack the other problem. And I think many people misunderstood my work. They thought I was a linearist by principle, but I was concentrated in those early years on the linear approach because I felt we should understand the linear before we went on to move to the nonlinear. And I think that sort of philosophy of taking the simpler problem and not ignoring the complexity, postponing the dealing with the complexity. And because linearity is so powerful, we can test the limits. We can do closed form sensitivity analysis. We can see exactly where our linear models break down. We can test them all to the limits, just like you'd test material in a testing machine in an engineering laboratory. We can really test them. We know what we're doing, and we know when we have to adopt more complex models. And I feel this is what is lacking in a good deal of the model building of today. I characterized many years ago, I characterized a lot of papers in hydrology as belonging to the category of figure 1 hydrology. Now, what I meant by figure 1 hydrology was, in those early days, was that somebody had a set of data, and then they cooked up a model, and then they said in the text, it can be seen from figure 1 that the model is an adequate, reasonable, all the words that were used, representation of the data.
And of course, we never hear that anymore, do we?
No, nowadays you don't. It used to depend on the thickness of the draftsman's pen. But now we have a new technology. Now we can bring in 57 parameters in order to confuse the issue and make sensitivity analysis more difficult. And we are still hearing at this meeting papers which are saying it is obvious that the model is a reasonable representation of the data. But where's the why?
Instead of the thickness of the pen, it's the thickness of the stack of computer output. Yes.
Exactly.
Well, where is the why? That really is what it comes down to. What do you think? I guess it leads to your concept of simplicity. Linearity is a form of simplicity. Parsimony is a form of simplicity. That's first you do the simple solution before you get to the more difficult.
Yeah, there are a number of them. I started to list them recently before a lecture I was giving. I probably can't remember them now. Similitude is a way for simplicity. If we look back for a moment to fluid mechanics and hydraulics, the use of the Froude number and the Reynolds number is a shrinking of parameter space, and therefore a simplification of the problem. A problem with 3 degrees of freedom is much simpler than one with 6. And that's what was done and led to the classical advancements in fluid mechanics. I have said very often that when we're operating at the catchment scale, we're operating under the difficulty is that we don't know the equivalent of our Froude number and our Reynolds number. That now has become a fruitful field of research. Of course, very interestingly, we had a sort of deterministic approach to this problem by Horton, followed by a stochastic approach by Shreve, and nowadays we have people working on both approaches to this particular problem. Again, looking for the simplicity, looking for shrinking. So similitude is one method of linearity. Simplification of the equations. We can linearize open channel flow, and we can reproduce every phenomenon of unsteady flow in open channel except the shock wave, which is inherently nonlinear. The other way that we can simplify that problem is to neglect certain terms in the dynamic equation, and we come up with the kinematic wave solution. The kinematic wave solution gets us our translation effects very well, but it produces too many shock waves. So we have to be careful in either way. That's what I say. We must know not only how our models work, we must know what their limitations are.
Yes, that's one of the problems, is knowing the limitations, or not even the limitations, knowing the domain over which they apply, because most of these approximations apply over a domain, which sort of leads into your paper you gave at the University of Arizona on scaling, when you gave the Chester Kisiel lecture, 6 years ago or so. That once again, this is an attempt to try to simplify, because if we try to model everything at every scale, it gets into your 57 parameters and 57 degrees of freedom, whereas if we try to get it scaling, we try to simplify so it applies over a domain. That was sort of your message at...
Yeah, that is. I like the example I often give. If we look at the fundamentals, water is a substance. What's hydrology concerned with? Hydrology roughly is concerned with the occurrence and the movement of water here on this planet. The occurrence of water, particularly its occurrence in liquid form. We go to physical chemistry, and physical chemistry will tell us why water occurs liquid, and why a neighboring anhydride from the chemical table, hydrogen sulfide, is a gas and not a liquid. Why this great difference between two neighbors in the periodic table? And the physical chemist gives us the answer. He said, that's perfectly simple. The water molecule is polar. It has a lack of balance. It's non-isotropic. So we're very happy. We say, I know why liquid water occurs. It's because it's non-isotropic. And we then say, how does water move? And we go to another shelf in the library, or we go to another person, and we say, we're going to up the scales a bit, so we're now talking about a continuum point. A point. It's not a Euclidean point. It certainly has some dimension. It's probably about 3-4 orders of magnitude different from the molecule we've been considering. So we now we master all the principles of material indifference and what is a fluid and what is a pure fluid. That's a fluid without memory. And then we write down a relationship, and we say, that looks awful complicated. We're trying to relate a shear here with a rate of strain here. And then we can sort of say, we better simplify. And how do you simplify? Let's try linearity for a start. We now have a Newtonian fluid. That's what it is. We talk about Newtonian fluids, and even the people dealing with nonlinear models treat water as a Newtonian fluid, but that's a linearization. That's where we get started. Okay, we now have a shear on this plane, and we have a rate of rotation with regard to another plane. So they will be connected now by some sort of a matrix. But of course, if these two planes are in different directions, that's a fourth order tensor. A fourth order tensor has got 81 elements. Or I'll give way. I'll accept that there should be symmetry, so it's independent of the direction. So there are only 36. Okay? Now, that means that if we wanted to connect these two, we would have to have 36 material properties that we would know. Let's hold up. I thought the Navier-Stokes equation, most people think it only has one, because it's always treated in the incompressible form. In the incompressible form, Navier-Stokes equation just has the dynamic viscosity. Even in the compressible form, it just adds the bulk viscosity. How do we get from 36 to 2? How do we make that simplification? In order to be able to start not with flow and catchment, not with the Songvenang equations, but even the basis of fluid mechanics. One assumption gets us from 36 elements to 2. That assumption is that the material is isotropic. So we're dealing with the occurrence of liquid water. We assume it to be non-isotropic. The movement, we assume it to be isotropic. Now, I mention this not because I think we can build all the way from the molecule up to the catchment or the GCM element, but for the lesson that we shouldn't carry prejudices from one scale to another. That things that seem to be inherently of the nature of things and governing everything at one scale may not govern at another. That the route to simplification at the molecular scale is not the same as the route to simplification at the continuum scale. And equally, the route to simplification at the catchment scale may not be the same as the route to simulation down at the pedon scale, or let's bring the vegetation into it and say pedon scale rather than patch scale, or at the GCM model. So the key thinking that has to go on here, we take that long line of magnitudes from the molecule up to the GCM grid scale, and there's over 20 orders of magnitude here. We want to look at that line and try to go in at certain points and get a sort of theoretical resonance, whereby by coming in at that particular scale, we will find a simplification. We will find simple laws, like Horton found by just plotting data which he had. So I believe if we're to make fundamental progress in hydrology and not be a lot of Pygmalions falling in love with the models they've created themselves, then this is the way we should go.
Well, it seems that sort of leads naturally into scaling, which is a hot topic. It's a buzzword today, and it's interpreted many different ways by many different people. It's like the question of what is a physically based model. If you ask different people that, they all believe in physically based models but have different definitions. Similarly, in scaling, what is, and as you know, there have been a whole series of meetings on scale problems in hydrology. How do you see the scale?
There have been a whole lot of meetings labeled scale problems in hydrology,
right.
but not really about the fundamental scale problems in hydrology.
What do you think are the fundamental scale problems in hydrology? Is it, as you were speaking, going in at different points and setting up laws at that scale, or is it the laws that connect those scales in some common thread?
Well, I think, let me put it this way. Most of what is talked about as scaling is just multiplication. I believe that we need something much more fundamental than that. Now, I think we've got to do a number of things. We've got to approach things a number of ways. I talked about going in at a certain scale and looking among the data for laws. Also, we can get hints about this by aggregating upwards from a micro scale. And this means that we take perhaps a deterministic law at a micro scale, then apply a statistical distribution in order to get a probabilistic law at the scale of interest. And this certainly, we may use this because we have to use it, because we have to have some answer, but this can also point us in the direction of maybe getting deterministic laws at this particular level. Equally, we can take a level at which we feel we know things, and we can disaggregate downwards. Now, in a very interesting paper on conceptualization and scale in hydrology, Vit Klemesh made the interesting remark that if we look at science, and we look at the sort of scales, we look at the human scale, and we look at larger and smaller scales, that man solved the problem of the planetary system before he solved the problem of the global system. It skipped several scales. Newton, based on the work of Kepler, Copernicus, and Tycho Brahe, we shouldn't forget this whole thing took quite a long period, he was able to produce this. Incidentally, let me put in another plug. Why was Newton able to get a good solution? Because he was able to use superposition. He was able to use linearity. Uh-huh. And it waited then for others to come along at the beginning of this century and say, well, now let's see what happens when you put in the additional terms. And this was done by Poincaré, and Poincaré produced the initial ideas, which everyone forgot about for 50 years and have now rediscovered as being the basis of chaos. But anyway, let's go back. Man was able to solve these problems about these vast astronomical differences before he was able to solve problems on a regional scale in his own planet. And equally, if we look at the...
Was that because he could measure the planets and he couldn't measure the Earth?
Probably he could measure the planets, and also because there was a simplicity there. Newton found the simplicity by taking Kepler's inverse square law and interpreting this in terms of gravitational attraction, a simple idea. But equally, as Vit Klemisch pointed out in this paper, we learned to understand atoms before we learned to understand molecules. So we should have no inhibitions about skipping scales in order to look. Ultimately, will there ever be an ultimate theory of hydrology? It is conceptually possible that we will be able to go by reasoning and by both deterministic and stochastic methods from the water molecule to the GCM model, completely go up and down that ladder just as much as we like. But I ask myself the question, and it's a geophysical question, which is going to come first, the completion of that endeavor or the end of the geophysical world?
Yes, very good question. Given the difficulties of the one and the certainty of the other, probably the end of the world will come first. So, getting back somewhat to our history of the mathematical models in hydrology and the interaction with the Eastern Bloc and with Kalinin in particular and his group in Moscow, which then expanded to the Hungarians and the Czechs and the Slovaks and the Poles and the other members. How much interchange do you actually think took place? In other words, how effective was this tool for communicating between the Eastern countries and the Western countries during the 60s and 70s?
I think it was vital. I think hydrology can be proud of itself that it did have one of the scientific breaches in the Iron Curtain. But that wasn't done automatically. We were given the authority to form this committee in mathematical models, and then we made certain decisions. We made the decision that the first symposium we were going to call together would be called in Eastern Europe, because otherwise, if we had called it in Europe or in North America, we would not have got the attendance of the Eastern Europeans. And that is the reason that we picked on Warsaw for the first symposium and held, as you know, the Symposium on Mathematical Models in Hydrology in Warsaw in 1971. Now that, to my mind, was a very important symposium. That was the first time that people from many different areas who had been sort of infected with this new approach to hydrology, they came together. They came together to present their papers, but they also came together to talk in the corridors and to react with one another. And I know from my own discussions with them that for many of the scientists from Eastern Europe, this was, in a sense, a liberation.
Well, I know that I was quite surprised when I read Cushman's papers, for instance, to see him extensively quoting U.S. and British papers, whereas we, of course, were not at all aware that Cushman existed until these meetings took place. And I think that's true, that we learned, and we also learned that they were thinking the same things that we were and doing some of the same things, solving some of the same problems. In fact, the Kalinin-Milyukov flood routing, which was their equivalent of the Muskingum, was a much better formulation because it had certain characteristics that they were aware of, that it was a pure linearization under certain circumstances. And they built it in such a way that it was, with the characteristic length and everything. So that committee met for quite a few years under the IAHS. and eventually became what is now the Commission on Water Resources Systems. And it seems to me has become more applied than theoretical, whereas our original part in the mathematical models was to get together the people who were thinking about new tools for solving hydrology. The commission now has evolved into a communication among people who are trying to manage water as opposed to solving hydrologic problems. Do you see that as the way that it has evolved?
I do. I think that committee on mathematical models might have been better off if it stayed as a committee rather than being a commission. But it's perhaps interesting to look back as to how it became a commission. It became a commission at the IAHS General Assembly in Moscow in 1971. And it was part of a compromise package. Walter Langbein had made a report on the reorganization of IAHS to break away from the traditional structure of dividing up the work of IAHS into a commission on surface water, a commission on groundwater, a commission on erosion, putting these into separate compartments. And he was proposing that, in fact, this should be abandoned and that we should tackle it from various points of view. And an obvious point of view would be this question of theoretical hydrology or mathematical models in hydrology. However, the membership wouldn't wear his new system, and they erected this commission. I think that was possibly a mistake. We would have been better remaining more informal. I think the great success leading up in the 60s, the great success in the 60s was the degree of informality. Just enough formality to allow the Eastern Europeans to take part, but in not more than that. We set up in those early days, as you remember, just for the purpose of organization, just for the purpose, perhaps it was even just to put some structure on the Warsaw meeting. But we divided among 3 working groups, one on deterministic methods, which we called parametric hydrology at that time, one on stochastic methods, and one on water resource systems. And what we had in mind here were things like the theory of storage and problems like this, following the Moran-Lloyd type of developments, which dealing with our inputs as Markov processes, and it produces some beautiful results as well as useful results. But and then when the commission was set up, we kept that division. I think we made a mistake there. We may have made the same mistake that the association was making, because as the years went on, it became clear that in fact the whole thing wasn't for everybody to be given a label which said he was deterministic, stochastic, or water resource system. The question was to take a problem and say, now, what mix between a deterministic approach, a stochastic approach, and maybe some optimization approach, what mix is required? But we didn't. We kept them in separate compartments. And as you say, they're always, it may well be that those interested in pure theory, as the years went by, sort of those interested in pure deterministic theory, pure stochastic theory, became less interested. So that in a sense, those who belong naturally to the water resources group tended to absorb or form the majority of this group.
Yes. Well, how do you think we could instigate this new group of hydrologists that we're really speaking for to do what we did in our day and create their own venue for getting together and talking and communicating? It seems to me that's a very important thing. Meetings like this are important, but they're much better if you have some informal group that get together on a much smaller scale than 7,000 people and communicate. So how do you think, what do you think is the best structure for doing something like that today?
I think I can only make a personal statement here. I'm at the end now of my career, but I think some of the same things still attract me. I'm very attracted. I'm curious about what are the essentials of the hydrological processes. But this doesn't mean I despise the application of hydrology, but rather I believe that if we can get a better understanding, then we will get better and more economic solutions to our practical problems. But my own personal interest is in this theoretical underpinning. I'm interested not only in finding solutions to problems, I'm interested in the aesthetic appeal of these. So you see, this sort of canon of simplicity that has been so important to me always is has an aesthetic element to it. Some way I feel that the simpler is more beautiful than the complex in subjects of this type. So, you know, it's almost a thing, and maybe this is just an old man talking, but why not begin all over again? Why not say now we have now got these very powerful computers, we now have these very large models. Let's start off again and see how, maybe it's a question that we should study not nature, but study what some of these modelers are doing. Ask her to look at this phenomenon of having models and bigger and bigger models, bigger and bigger computers, and not really tested to the limits. And
well, our problem there, though, is we'd have to take a course in abnormal psychology, wouldn't we?
well, I don't think we should go quite that far.
Well, it would seem to me that perhaps along with having the PhD sit on the riverbank for a year, another thing would be to forbid any candidate to use a computer until after he gets his degree.
That's a bit extreme. I wouldn't go along with that. But that allows me to tell my Copernicus story.
Yes, I was going to lead into that.
yeah. Well, I gave the society lecture to the European Geophysical Society recently, and I was talking about this question of the search for simplicity, and I said to them that I had an occasional worry, occasional thought that recurred to me, not really a worry, that's the wrong way, but a speculation, that if Copernicus in his day had had two things, that things might be different now. That if Copernicus had had a large computer, but more particularly if Copernicus had had the computer mentality of many a model builder, and I applied it to all geophysics, not just to hydrology, that the position might well be that we would be sending people to the moon, not on the basis of Copernican model, but on the basis of superimposed epicycles according to the Copernican system, because it's quite obvious that in the Ptolemaic system they added epicycle after epicycle. So one could imagine this modern Copernicus just saying, I want to add 3 more layers of epicycle, will you please give me a bigger computer? The thing is that the Copernican model did not fit the data better than the Ptolemaic model. It fitted it almost as well with considerably fewer parameters. That was the criterion, that was the nature of the Copernican revolution.
But the Ptolemaic method was a linearization, so that should have appealed to you also.
Maybe that's the subconscious reason why these thoughts recurred to me.
Perhaps so. Well, it seems to me that we have now a generation of hydrologists who are being strongly influenced by global hydrology. It's interesting that the the first real good study of global hydrology actually was by Kalinin that you mentioned.
Exactly.
His book was quite excellent, and yet most of the global modelers don't know of that work. But we have a whole group of hydrologists, or people getting degrees in hydrology, who have been fed on global modeling, in which the hydrology is almost, you might say, washed out, if we can coin a term. And that in terms of actually knowing hydrology, they don't get a chance. What do you think is going to come out of all this global modeling, GCM, basin scale translation from the GCM down to the basin scale?
Well, I've been involved in this myself with these concerns. In fact, I was a member of the organizing committee for the first World Climate Conference in '79, and I chaired the organizing committee for the second World Climate Conference in 1990, and acted as liaison between the International Council of Scientific Unions and the World Climate Research Program for many years. So I have been concerned with this particular problem. But more relevant than that, we in our own Centre for Water Resources Research in University College Dublin took part in an interesting exercise funded by the European Commission. And this was an exercise in which four of the leading, three global climate modelers and one notable team in mesoscale modeling came together with four hydrological groups with very different strengths. We came together to try and compare our models and see can we reach any conclusions about what was the best way to go. Now, the interesting thing was the length of time that it took for us to understand one another. And this is a recurring problem which comes to my mind, that people think that science has a common language. Well, maybe it's right to say it has a common language, but there are many dialects within that language. And as we know, in any of our own cultural languages, it is very often as difficult to understand another dialect of your language as possibly a foreign language. And that is one of the problems. What we did in this particular project was we took a certain set of data, synthetic data, and we all applied our own models to it. It was after doing that exercise, we did the first exercise, and then we suddenly realized that we had all made some, you might call them elementary errors. One of the problems that when we designed this experiment, it was designed by the climate modelers, and they allowed a spin-up time for 2 months. That was grand. That's what they'd always used. And they were quite sure after 2 months everything had settled down, and we could now look for an equilibrium condition. But of course, that was only true for the atmosphere. And when we put in properly coupled hydrologic models, we then found, in fact, that you would run through, spin up for 2 months, run through for 12 months, and you would get a result for the water balance. You could get, we were given the precipitation, but we could get the actual evaporation and the runoff throughout the year. Trouble is, of course, that we didn't get equilibrium. The soil moisture was different from the beginning to the end. And in fact, what was the cause of this? The fact that the ground operates on a different time scale from the atmosphere. It doesn't reach equilibrium nearly as quickly. In fact, once again, of course, you don't have to ask me what I did. I took a linear model to explore this, and I discovered the interesting fact on it. I linearized the Richards equation, and I was then able to make an estimate of what the storage delay time was for different depths of soil layer, and all the models have different depths. I found for the linear, in fact, that the delay time was directly proportional to the depth of the soil layer. So GCM's different depths would definitely mark. And meanwhile, while these people were finding out empirically that they got a balance at the end of the second year, I was predicting that for all their models, the delay time lay between 1 and 2 years.
Uh-huh.
So,
There comes your linear assumption again.
yeah, as a first step.
Yes, as the first. Well, it puts limits on things.
I think that's a very important word you've used, putting limits on things. We talked about the question of methods of simplification, and we talked about a few of them. But another one is to take limiting cases. We have a differential equation now that we want to solve. And it is rather difficult to solve this analytically in its full form. And of course, we can just write out the program, crank it. But this means we have no general result. But we can look at that equation and we can say such and such a parameter lies between, sometimes we can say the physical limits, not even what's being measured in the field, but we can say there are certain limits. For example, we can say that the horizontal conductivity in a soil lies between 0 and infinity. That appears to be a tremendous range. Now, when people start to look at the effect of heterogeneity on soil moisture, and this is a key problem in upscaling for GCM models, most of the early work was done by taking independent soil columns, finding out what the evaporation or infiltration was at the surface, and then applying a statistical distribution. Now, what are you doing there? You're assuming that the horizontal conductivity is 0. There is no intercommunication between the columns. What is the opposite to that? The opposite to that is to say that the horizontal conductivity is equal to infinity. What does that mean physically? Horizontal conductivity is equal to infinity. That means it cannot sustain any gradient, horizontal gradient. It will, at every level, you will have an equipotential line. Recast the Richards equation, not in terms of moisture content, but in terms of potential, and you again have a one-dimensional equation. Your boundary conditions are difficult. Your initial conditions must be in equilibrium. But we can get 2 one-dimensional solutions. A one-dimensional solution for horizontal conductivity equal to 0, and a one-dimensional solution for horizontal conductivity equal to infinity. And the limits are quite narrow, and interestingly, the limits both indicate a lack of sensitivity to the form of the statistical distribution used. You can take a U-shaped distribution or a unimodal distribution, and in spite of them being so different, we get a very low sensitivity. So here we have some guidelines about how to tackle the bigger problem.
That would mean then that one shouldn't try to determine the statistical distribution from data. That would be going down the wrong track because you couldn't identify, based on the data, what the statistical distribution was.
You couldn't distinguish between them based on the data. And of course, how do you choose? Well, once again, of course, I will be unpopular with certain people, and I would say I would choose the gamma distribution because the algebra is nice.
Yes. Nice.
The moments have a simple form. But that's not the only reason I like the gamma distribution. You know, we can go away and read our books on probability and statistics. And of course, particularly in the early days, when I was working, the standard books, they were all about the normal distribution. We had all the reasons why the normal distribution was the distribution. And then when we got out into hydrology, we found, well, things weren't symmetric. We had asymmetric distributions. And we went to this empirically. I mean, what are we going to use? Logarithmic, gamma distribution, log gamma, what are we going to use? And it's interesting that only once have I come across a, a justification for the gamma distribution equivalent to the classical justification for the normal distribution. And this was from Velikhanov, a Russian hydrologist, statistician, writing, I think, in the 1930s. And Velikhanov pointed out that if we take the distribution, which is often in the textbooks, of taking a series of Bernoulli trials with p equal to 1/2, and then applying the law of large numbers, we get a normal distribution. Velikhanov took the problem of taking a series of Bernoulli trials with p not equal to 1/2. Guess what he gets?
Not a gamma distribution.
Yeah.
How about that?
Yeah, and it will go, according to the law of large numbers, it will go ultimately to a normal distribution, but long before it goes to the normal distribution, it goes through the gamma. The gamma itself will go to the normal. We take a cascade of linear reservoirs like Nash did for catchments, or Kalina-Milyukov did, and we take a finite lag and make the lag of the individual reservoir become infinitesimally small, and the number of reservoirs become infinitely large, their product remaining constant, we get pure translation. So we come to symmetry in the end, in dimensionless terms. We come to symmetry. Mm-hmm. But there is we have all this talk, all this use of gamma distribution, but that's the only instance I've seen of a justification of this.
Theoretical justification.
So you've learned something from this talk.
How about that? Well, I always learn something from you, Jim, even if it's just our history of hydrology. Well, where do we go from here then? Given that we now, you and I both, are sort of at the end of our careers, what would you say to the young hydrologists coming out today? A, what should they look at? B, why should they look at it? And C, how should they look at it?
I would say to the young hydrologists, learn your hydrology, of course, but be curious about other subjects. And there's one thing that worries me with all our information systems and all their wonderful tracing systems, that in fact we're going to lose in science. What are we going to lose? We're going to lose all the things that in the past were gained by browsing in libraries. You're going into the library, you're going along to the hydrology shelf to look for a particular book, and on the way, a title catches your eye. Something from mathematics or systems theory somewhere else. And you take that out as well. I don't know. Well, of course, you can say to me that you can build that into your various literature searching things, but I'm not so sure that it's going to be as easy for the student of the future to do this. Electronic browsing, I don't think, is going to be as easy or as efficient as the browsing which we did in the library. As I've already said, when I got these first ideas about linear theory, I went off and read the theory of electrical circuits. Later on, as we come forward, I went reading books on automatic control to get the idea of systems and feedbacks, etc. And you get things in the strangest places. For example, let me give an example of an analogy which I've used in the past. We're looking for laws at the catchment scale. And we could say, well, let's take something from hydraulics. Let's take it that in a catchment, the water is falling under gravity. So here we have gravity as the dominant force. So having had our training in fluid mechanics and hydraulics, we say, well, this should be a Froude number. And we can then do, as suggested in one or two papers in the past, we can then relate the peak discharge to catchment area as being proportional to A to the 3/4. That's the Froude number tells us that. We look at some of the classical data assemblages in this, and we find that's, well, it's not quite 3/4. We look at the British flood studies or Benson's work or any of these, and it looks more like 2/3. Now, the analogy that I take for that, let's keep that in mind. We think it should be 3/4 and it's 2/3. I want to go to biology now. And we have lots of things in myths which talk about conversations between the mouse and the elephant. And if we look at the size of animals, from the mouse to the elephant, and we ask the question, how much energy, what's the relation between energy output and mass in animals going from the mouse to the elephant? People have postulated, well, that should be rather easy. The mass should be proportional to some length scale, and since energy of mammals depends on the oxygen that we take in across our lungs, which is the surface, that should be proportional to the square. So we say, right, well, that indication, then the energy output should plot as a straight line on log paper with a 2/3 slope. Right, let's get the best data in the biological literature and we plot it. And it plots along a straight line. But the slope isn't 2/3. The slope is 3/4.
Uh-huh.
They have a different problem. Now, an answer was produced by a man in the early 1930s called Kleber. It was, first of all, Kleber's empirical law, and then somebody said, well, these are all different types of animals from the mouse to the elephant. They all arose during evolution. And what was the key problem during evolution? Key problem during evolution was to catch the prey and avoid the predator. So the question is that in the course of evolution, the question was your ability to run without your leg collapsing under you. And this depends on Euler's theory of buckling, because bone is exactly the same strength in the mouse as in the elephant. That's something that doesn't scale. Bone is exactly the same. And if you apply Euler's theory of buckling and the simplest form of buckling, you get the prediction of 3/4. Now, what relevance is all that to hydrology? When we look at the lungs and the breathing of the animal, we are looking in a short time scale. We're looking at the present activity. Evolution took place over hundreds of years. It's the same thing in hydrology. When we look at a catchment and we look at a flood, we're looking at a question of hours and days and weeks at the most. Whereas the laws that govern catchment action are in geomorphological time. So the question of scaling here, this is an example of the sort of thinking we want in scaling. That even when we're talking about linear scales, we have to be sure we're thinking in the right temporal scale as well. I'm sorry for the long discursive talk about that, but this is the sort of thing that I recommend the young hydrologists to think about if we're going to make real progress.
Well, that's long discursive conversation is quite good. In fact, it sort of reminds me of Eamon Nash's statement that if he were ever to become a professor of hydrology, which he did, and he probably didn't live up to his statement, that he would never allow a student to take a course in hydrology, but he would force them to take other courses such as math, physics, chemistry, biology, and then their hydrology would be in special studies where they put all those together to solve problems. And I guess that's sort of what you're saying here.
Oh, not quite.
Not quite.
No, I believe there is an essential core of hydrologic thinking. I think that Eamon may have said that because he never did hydrometric survey work.
Maybe he never string gauged. Yeah, we're string gaugers in the USA. We don't do hydrometric survey work.
Sorry, yeah.
When will you people ever learn to speak English, huh?
Well, I have to quote an Irishman on this. It was George Bernard Shaw who said, England and America are two great nations separated by a common language.
Yes. Well, that's true too in hydrologists
It
and
is.
such. If you think back to my statement earlier that when you asked the person about what is physically based hydrology, that each of us in that group that you asked would have answered differently. And in fact, I answered differently, certainly, than the person that you asked the question of. And on many other things, and I think the scale problem is another one, where everybody says, I'm doing scale problems in hydrology, when actually they're going off in diametrically opposed directions. And I think in many other cases also, the physical stochastic, which was a buzzword for a while, which meant different things to different people. So I think that one of our problems is communication and dialects, but it also is just semantics. We have different definitions for the same word. We're speaking the same language and meaning different things, not because of dialect, because of interpretation.
Yeah.
So well, what do you think then should be a core for how to think, to get the students how to think about hydrology?
Well, first let me agree with what you say. We have this problem not just in hydrology, between hydrologists. We have it between the scientists. We have it between ourselves and the meteorologists, ourselves and the oceanographers. We have it between the physical scientists and the biological scientists. And the trouble is not that we don't understand what the other is saying, is that we think we understand. Because, as you say, we attach different meanings of words. And the danger is not a lack of comprehension, but a mistaken comprehension. And that is very, very difficult to cure. And I think the cure to that is only on the basis of working together on problems of common interest. Actually, we must have an actual problem, whether it's an intellectual or a practical problem. But we have a practical problem that is the basis of the discussion. Now, when we do that and we come together, it may take some time, but we will eventually work it out. It's like the question of, we can talk about interdisciplinarity, and this is probably part of the problem. And we can talk all we like about it, but that doesn't produce it or produce any results. Interdisciplinarity only works in regard when it's focused on a particular problem. Now, one of the things I've been concerned with the International Council of Scientific Unions, which is concerned with the whole of science, and one of the concerns there is the question of the building of new partnerships to face new problems that we are in science today. And I think we have the same problem in hydrology. We have new problems and we need new partnerships. But I'm becoming more and more to the conclusion that we have to be very careful what we mean by partnership. And they've got to be equal partnerships. I think there's a tendency, both within hydrology and hydrologists operating with others and others cooperating, is to say, right, we're going to build a model. We know how to build a model for this particular problem. And then we come to a certain stage and we say, oh, we perhaps should ask a biologist what the value of this parameter is. So we use other people in other disciplines as suppliers of parameter values. Now that is not partnership. That's trading. That's buying in. And even when we do go further, we tend to have junior and senior partners. And I think partnership to work must be equal partnership. Now that doesn't say the same amount of work has to be done by everybody. It doesn't mean that the same amount of input is, but it as it were, calls for a parity of esteem. A real partnership based on parity of esteem. That's one of the keys to it. And that's the thing that even if young hydrologists are not interested in the sort of thing I'm interested in, they are interested in the model building business, then they must cooperate with others, but they must cooperate with them on this equal basis. And this means, in regard to model building, that you shouldn't go down to the 11th hour and then ask the biologist what's the parameters. Neither, I think, is it feasible to say from the very start, let's get the biologists in and build a model together. I don't think we'll ever get anywhere on that. But I think what you have to do is say, what sort of a model do I want? And when you have your first draft of your model and your first idea, rather than go on refining it yourself, you bring in the meteorologist or the biologist in those later stages. I think this is very important.
Well, this is much like my problem as a statistician, that people always run their experiments, then when they run into trouble on interpretation, they come to me and say, how do we interpret these data? How do we analyze these data? And I say, well, the first thing you do is you ask how you're going to analyze it before you collect it. And quite often people don't. And the same thing here. You've got to think early on what you're doing the model, if you want it to be a model, for. And then you design your procedures to get your result rather than waiting until the end and finding out it won't work. That's quite true. So a friend of mine used to say, it's not what we don't know that hurts us, it's what we don't know we don't know.
No, exactly.
And quite often that's the case. Well, I also find, at least in my opinion, that this cooperation, the way you're discussing, is much easier for the graduate students than it is for the faculty and the senior people. That when you're at the graduate level, you're more liable to be talking to the guy in the next room or communicating with him. Quite often you don't really know what the answer is. That's why you're a graduate student. You're given a problem to solve.
Professors always know the answer.
Yes, and professors always know the answers. That's right. There are so many things they know which aren't so. And I think that therefore somehow, how maybe is what I should ask, how can we stimulate the graduate students to continue operating as a graduate student even when they become a tenured professor? How do you think we could accomplish that?
Maybe we have to do something about the university structure. Maybe we have to get away, as many universities are trying to get away from the old traditional departmental system, but it's not easy. It's not easy at all. Perhaps I go back to something which is not concerned with hydrology at all, but when I moved from being professor in Cork to being a professor in University College Dublin around 1970, the head of my water quality lab went to another job shortly after I came there, and I recruited a biochemist. He was the best qualified person. And then I decided, now I'm a biochemist, why shouldn't I get a biochemist to teach my civil engineering students? So in 1970, quite some time ago, I got through the academic council that there should be a course compulsory for all civil engineering students in biology. But I didn't call it biology, because if I'd called it biology, it would have been taught by the biology department. And because it was being taught by another department, the students wouldn't have paid any attention to it. So I was in a very real difficulty. So I suddenly hit on the answer. I brought forward to the faculty a proposal for a course called Introduction to Biosystems. And of course, since the word systems was in, it must be in the engineering department. And it was taught by a biochemist. The examination papers were sent in our system to both the extern examiner in civil engineering and the extern examiner in biochemistry. But these students were then taught everything from the cell, a full year course, everything from the cell to the global environment. And I think that's one of the best curriculum changes I made.
They were introduced to scale problems in hydrology early on. Well, I think that the single thread or message that I've gathered from all of your history and your career is a stress for simplicity and parsimony. and if that's your guiding philosophy in how to solve problems, solve, as you say, a small problem first, linearize first, find out how the system works in the general sense, and then only study the more complex problem to find out how it differs or deviates from the linear.
That's right. The principle of parsimony was, of course, enunciated in the 14th century by William of Ockham. And his put it in the form ensia non sint multiplicanda. And since many people don't follow classical things, I usually translate that for my students.
You'd better for me.
And the translation is, don't have too many damn parameters.
Well, there was damnation in his statement. But that's true, yeah. Occam and his razor.
That's the modern form of Occam's razor.
Yes. Well, and I think that's a good message to leave. I think that we have almost gotten to the end. Do you have any final concluding remark that you'd like to leave on your philosophy, what you think needs to be done, where you think the world should be going, at least the world of hydrology?
Oh, no, I think the only thing I want to say is that looking back now over my career in hydrology, it has been satisfying. It has been satisfying because of the work, and it's been satisfying because of the people I've met through it. But there's one thing above all, and I don't know whether this sort of has been because of my particular attitude towards this particular type of searching, but above all, it's been fun.
And I think that's the final message. Everybody who is in hydrology should have fun, because we're in such a fun field. Thank you, Jim, very much for the interview.